Test, test, test. Test, test, test. Test, test. All right, so we're going to get started. Sorry, there seems to be no way of me to displaying what's on my screen here, so I have to use the little computer here, or wait an hour for people to come and help. So I'll choose the latter. Okay, so we've started looking at numerical methods or numerical routines. And this lecture is going to be one in a series of lectures where we look at particular numerical techniques and show you a little bit what the basics of them are. And then we'll show you how to use them in your code without having to code them in. In other words, the next 4 weeks, we're basically going to be lazy programmers and using libraries of people that have already coded in what we want to do and write some wrapper code. This will make you a much, much more productive scientific computational person. So we're going to look at root finding and optimization. Those are two things that happen quite commonly in computations, and even if they don't, they illustrate a lot of the points that you will find happen when you do numerical calculations. So sometimes you want to solve an equation numerically. This happens. And if there's just one unknown and one equation, we could write it as fx equals 0, and that's what we want to solve. And so if x satisfies the equation, we call it a root, and that's why we call this root finding. So this can be generalized, obviously, to more than one variable. You could have, say, 3 variables, x1, x2, x3, that satisfy a number of relations, f1 equals 0, etc. All right? We would still call that root finding. We find the solution of these. We'll look at the one-dimensional case first because it's easier to solve, and it shows a lot of the intricacies in doing this numerically. So this is nice in 1D for a number of reasons, but one of the nice things is we can always kind of know if there's a root. If this is a smooth function f, and I've plotted it here from -3 to 3, and you can see where it's 0. But of course, we can only see where it's 0 because we've had the computer calculate a whole bunch of points to make this curve. So it's a bit cheating, right? If each point on this curve took a day to compute, we'd never do it this way. So it's just for illustration. So we want to find a way of finding this root where this guy is 0. Where this guy is 0. While minimizing the number of evaluations of this function. Okay. But what's nice about 1D is that if I know that the function is negative at -4, as it is here, and positive at 3, and assuming it's a smooth or at least continuous function, then I know there has to be a root somewhere in between, right? And so the strategy will be to zoom into that root until we're close enough or until we've found it. But we know there is one. This is something that we'll lose when we go to higher dimensions, where you can't just take a couple of points, evaluate a function, and know for sure that your root, that your solution lies within those bounds. Here, we know there's a solution as long as we know that this function is continuous. So we call this bracketing of a root. So A and B are a bracket of the root around the root. Somewhere in between that interval, we know there is a solution, and we know it by just evaluating FA and FB. So we're going to try and refine this. Now, even if this is true, even if we have that, we must first find a bracket. Without that, we're pretty much lost. And so this is more of an art than anything else. You kind of have to know a little bit about your function. If you know, if you can spare the cost, you can plot a function and get an idea of where things are, right? You could make a conservative guess, say, okay, I want to know the distance of the Earth and the Sun. Well, it's going to be somewhere between a kilometer and the size of the universe. That's a conservative guess, right? If that's what we wanted to know. So you can do that and then start slicing it up and finding where a real bracket lies. This can take a while, so knowing more about your function helps. You can also just go crazy and say, no, I'm just going to guess. And if it's not bracketed, I'm going to increase it. So go the other way around. Again, this can take a long time. And of course, it can take an infinite time if there's not actually a root. So there's some cases where finding brackets are especially hard. Here are some troublemakers. If you have a function that has a root, so it's 0 there, but it doesn't actually change sign because it also happens to be a minimum, you're not going to be able to even bracket this root. There'll be very few numerical routines that will actually tell you where this root is, okay? Because you can't bracket it. You could have roots that are just below 0. That's the second one. And so they are easily missed. And you could have a non-continuous function. You could have a singularity. And then even though you have a change of sign, you would still not find a root because it doesn't exist. Okay, so you have to know a little bit about it. But suppose we do. Suppose we found a bracket. What do we do? I'm going to look at a few variations on how you now zoom into this root. Bisection, which is the easiest one, but not the fastest one. Then a secant or false position, and we'll look at Brent and Newton-Raphson too. Okay, so they all converge differently. They take a different amount of time. They take a different number of evaluation of the function. There are some specialized routines that I won't go into if f is a polynomial, or if the equation you're trying to solve might be an eigenvalue equation. For that, you don't want to use these general solutions. There are specialized routines that can use linear algebra properties that are much better at finding eigenvalues than doing this, even though the eigenvalue equation would in principle be solved by this. You don't do that. Okay? So bisection first. So suppose A1 and B1 are my initial bracket. I'll slice that interval from A1 to B1 in half, find the midpoint, and I'm just going to evaluate what the function is at that midpoint. Okay, so I'm going to find that this is now positive. Now I'm going to change my bracketing from A1 to that midpoint because that's still a valid bracket, right? A sign change happens there. So there we go. This is my new interval. I'm going to do the same again. I'll take the midpoint. Now I see I have to take A2 as the next. So A2 to B2 is now the next interval. And so this way, I get closer and closer to the true value. Right? Now where do I stop? How many steps am I going to take? 3, 10, a million. So this all depends on how accurate I want to have this solution, right? If I need the solution up to this tiny precision here from between A3 and B3, say that's 100 or something, then I can say I'm done. If I need it up to machine precision, and you're asking for trouble there, but we talked about machine epsilon, I could go on until A3 and B3 or AN and B3 are essentially the same number. But that's going to take a long time. It's going to take a lot of function evaluation. So am I really willing to wait that long? Does it make sense? So you're going to always put in a tolerance. You're going to say, I want this up to a certain accuracy that I am satisfied with. This could be a relative accuracy or an absolute one. Absolute would be the actual interval size. Relative would be the interval size divided by, say, the size of the midpoint, right? Because you want to be able to make this balance of cost and accuracy. So because we want to minimize the number of function calls, we're going to look at a few other methods that are faster in terms of how they converge to this root. So false position is another one. It kind of does a funny thing. It makes a linear interpolation between those 2 points. Remember, we've evaluated A1 and B1. We've evaluated the function there. We know those 2 points. We can draw a line, and we can use that line as an approximation. We don't know how good it is for the next point. So here it is. Here it is, right? So we're going to say, okay, that's our next point. We're going to see if the next point is positive or negative, and then we change our bracketing. So it's similar to the other one, except we use a linear interpolation. So we use a little bit more information of stuff we already have, and typically when you use more information, you have to compute less. So here's my new one. Do it one more time. Another linear interpolation. There we go. I think that's right. So that's another way to get there, and it gets there faster. Okay. So so all of these just evaluated functions. There's also ways of using the derivatives to get there faster. There are ways to use, rather than a linear fit, an exponential fit. There's ways to use even higher fits. Inverse quadratic fit is what Brent methods uses. So different fits use the information you already have from evaluating these functions to make an approximation of the function and get a better estimate for where your root is without doing more work. That's why you don't get there faster, but you do evaluate less. You get there faster with less evaluations of the function. Okay. But then another very popular one, and a very nice one that really is fast, is Newton-Raphson. So this one uses the derivative. You can imagine that you might be on you start at point x1 as sort of a guess, a wild guess. You take, let me take the derivative and follow it and see where the tangent would cross the line. It's a little bit like the linear approximation that we just did, but we only need the point and its derivative. So we only need 1 point. And then we'll say, okay, that's our next point. And we'll see what happens there. Well, it's not quite a root yet. So I'll say, okay, let's do the same thing at that point. Take the derivative and see where I get. You can kind of see this went very quickly to the right answer, right? This is very accurate already in just 2 steps. More accurate than the other ways. And it is because we're using the derivative to get there. So it converges faster. It converges quadratically rather than linearly. So you'd say, well, why don't we always use that one? Well, it has to do with convergence and stability. So here are 6 different methods by their names and how they converge. So the bisection, and I mentioned the convergence as how the error changes in each step. So basically, if you think of the bracket, how much smaller the bracket gets every step. So with bisection, it's always 1/2, right? The size of the next interval always 1/2. In the false position, it's some sort of combination of either 1/2 or 1.6. So 1.6, a higher number, is better because your error, once it starts becoming smaller, if you take it to a higher power, it gets smaller faster, right? So that's the convergence. So you want a high power. Newton-Raphson, without much tricks, is quadratic. So every time your interval or your error decreases by a square. So that's why it's so fast. The reason you don't just use it like that is that it can be unstable. So I'll just go back to this guy here. Oh, here. If we started over here, you can imagine that you would be shooting yourself all the way to a very large negative number, where this function might well be doing something wild, like going up like crazy, and you could actually, rather than getting your error become smaller and smaller, you could just diverge to essentially infinity, right, if you went on. So the tangent can be quite off. Sometimes that it's not a good way to get to your root. So what you want to do in practice is combine these things. So you'll want to do some bisection to get close to a root where your derivatives don't vary too much, and then you use Newton-Raphson to zoom in very quickly to the actual accuracy that you want.
Also on the assumption.
Absolutely. So you have to be able to evaluate. If you can't evaluate the derivative, you can't use it. But if you have an algebraic form of your function, then you could in principle get the derivative. So we should now start coding this in, but as I said, we're going to be lazy in this little section of the course, and we're going to use libraries for this. So this is a time to introduce the GNU scientific library. We've seen it in examples of makefiles, just because we had to put something in, but we're actually going to use it now. And so the GNU scientific library is a very useful C library. So it's not C++, it's C. It has a lot of useful scientific routines. Most of them are fast enough. They're not all optimized to the nth degree, but they're all fast enough to do your bidding. And so they can do root finding. They'll have like Brent methods and others. Minimization, sorting, linear algebra, fast Fourier transforms, integration, random numbers, statistics, Monte Carlo integration, ODEs, polynomials, special functions, vectors. Basically, they have pretty much anything you might need. Now, that's good. So we're going to use that. Here's an example of root finding. And because this is now C, a lot of the niceties that we might have now gotten used to in C++ and the object-oriented way of notating, we're losing this, okay? And I think it's good to see this. You might find a C++ wrapper library for GSL, which you might be inclined to use. But I think it's good to try and use the C version, because C++ is sort of a superset of C. You can always use a C library in your C++ code, and this makes you makes the number of libraries that you can use larger. So for this case, we have a function. Here's our example function. It takes a couple of parameters by a void star pointer. A void star is a pointer to anything that you might want to do. And so in this case, we will pass something in that is of type struct param, where I have a v, w, a, b, c, and they're parameters that I put into the equation that I'm actually solving. So because it's this pointer to anything, I have to tell the code that this is actually the right kind of thing, so that I'm taking this anything pointer and I'm converting it to a params pointer, and now I can access VWA. This is a conversion. It doesn't do much, but it just tells the compiler, trust me, this is a params. And then in the main code, we're going to start with our bracket, x low, x high. That's our initial bracket. We're going to set our parameters here. And then we have to do a couple of things because the GSL library tells us so. So it's going to be very important to start reading documentation of libraries rather than just start coding. The GSL is well documented. It's so it'll give you examples. It'll tell you what things do. But in this case, what turns out to happen is we have to create a solver objects. But because it's C, it's not really an object. So it's going to be just a type with a pointer. And we're going to create this object with this GSL root solver alloc right here. We're going to tell it what type of solver we want. So there's a bunch of extra things, GSL, root, F solver. Here's the heart of the matter. We're going to use the Brent method, which is a particularly good one. It's this inverse quadratic one. and doesn't need the derivative. And then we have to wrap our function into something that the GSL library understands. So a GSL function. And then in that function, we set the function to the example function. We set the arguments, the parameters to the arguments. Okay? Then now we can call our solver. Here we go. Solver, wrapper, x, low, high. And that just sets our solver up. We haven't done anything. We've basically created this object. If this were C++, we'd have some sort of constructor doing this for us. This isn't C++. We have to do a little bit more work. It's the same work every time. It's not very hard. You just look up in the documentation how it goes. Now we want to start zooming in. So we have set up our initial bracket. We have set up the function. We have set up the parameters. This solver knows everything. Okay? It acts as an object, just not implemented in an object-oriented way. And then we just iterate. We're just going to say, oh, let's try and iterate at most 100 times. Do one iteration. I'm going to look at what the value of the root is currently. So I can find the root. I can find the lower and the upper bound. And then I'm going to check whether the difference between the upper and the lower bound is now good enough. So what I should do is probably say, okay, the difference between the two has to be less than some tolerance. For that too, the GSL has a little function called test interval, and it just tests whether this interval between x low and x high is between 0 and has an absolute accuracy of 0.001. So you can give a relative one or an absolute. In this case, I did absolute. It really takes this idea of not coding anything yourself too hard, right? Even this last part, you go, well, why don't I just do that? And you could, but why would you? The chances that you make a little mistake, especially if you're doing it relatively, are just like, why would you take the chance? There's a function that does it, and it puts its status in. And if status is true, it's false, it says, okay, we're good, we're ready.
Let's offer.
Okay, so this is just, it's going to print out values as it does iterations, right? So it's going to print out the iteration number, the left part of the bracket and the right part of the bracket, the root that it thinks. It's going to print it out. And this top line here is just a little header that will tell us what it is. Okay. So,
Inside the sign.
yes. So if you remember the syntax of how we get member variables from a class, we had this arrow notation, right? So P arrow A is just the A that is in P, right? So P is a struct right here, or it's a pointer to a struct. So you get access to, so P contains a whole set of these. PA is one thing, PV is the V that is in it, PW is the PW in there, the PB is the PB, the PC is the C that's in there. So this is just a function using these parameters, okay? It's some arbitrary function. It's actually the function that was in the graph on purpose. So it just, that's all it does. It takes those parameters and computes the value of the function. Okay? So if we want to compile this, on Sinet, you'd have to at least load the GCC module to get G++ and a GSL. And now there's various GSLs. Some are not for the G++ compiler. Some are. There's different versions. If you want to know which ones, you can do a module find GSL, and it'll give you the list of possibilities. GSL/1.15 GCC will give you the one that's compatible with GCC and is version 1.15. And then you can compile this code, say it was called GSL rx.cc. I can compile it, I can put my normal flags, and then because we're on Sinet, we're on a shared cluster where software is not installed in the standard location, I have to tell the compiler where this header file is. So if you look here, GSL/GSL underscore roots lives somewhere, and we have to tell it where it lives. So it lives in Sinet underscore GSL underscore inc. That environment variable has been defined in those modules. That's what one of the things the modules do. That's the header file that only says what functions there are. It doesn't actually have the code for the functions. That's in the library. And so in the second step, we always have to link in the library. GSL right here. And again, we have to say where this library lives, and it lives in Sinet GSL lives. So -I adds to the include path, -L, capital L, adds to the library path. And I'll look there and I'll find it. Okay. Now, it turns out that the GSL library depends on another library called BLAS. And so in this case, we have to link in GSL CBLAS too. If you don't, you'll get all kinds of undefined variables or undefined references. This is how you link with it. Yes. So typically when you're linking, you want to link in what you need and then link what that needed and then link what that needed. So it's kind of hierarchical. If you first do CBLAS and then GSL, it tries to link in the CBLAS, but it's too smart for its own good. It says, nothing's needing CBLAS yet, so I'm just going to leave it out. Next thing you know, it's linking in GSL. GSL says, I want CBLAS. I don't have it because we'd already dropped it. So it's a little bit too clever. So the order does tend to matter. And that is not nice, but it is how it is. Okay, so I have a little slide to remind you, because now we're getting quite a few moving parts, of how you build with libraries and how it all fits together. It's not going to get any more complicated than this in our course, but this is it. So just to recap, and this is the stuff you put in your makefile. When we're compiling, there's a compilation and a linking state. The compilation is here. All these .c, or there should be .cc files, get compiled in .os, each one by one, right? Although it's one yellow block, really is just one by one. They might need some header files, .h, but they include them themselves. So don't compile the header files, they just get included. So they depend on them, but they don't get included in the compilation on the command line, they get included in the code. Once I have all these .os, I can take them together and link them to the executable. But if I have libraries, I have to also link in those libraries. On Linux, there's two variants. There's the static ones and the dynamic ones, and I'm not going to go into the difference, but they're either called .a, .so. Even though that's what they're called, this is not how you link them in. You just link them in by their name, -L GSL, for instance, right? One of these header files over here, though, will correspond to these libraries. So the header files will be included, but they just contain what the declaration of the functions are, right? The libraries themselves contain the implementation. So when we're using libraries, we have no choice but thinking of this linking stage, because we have to specify it. If we just have our own code, we could combine the compilation and linking stage, although it's not very good, because we have to, every time we recompile everything, we can do that. With libraries, we have to link something, and so that's what happens. Clear? All right. This is what you try to tell your makefile to do. All right. Multidimensional root finding is harder. And it's harder because you can't bracket your root. Imagine this. Oh, I don't know if I had a nice picture once, but imagine your root lives somewhere in three-dimensional space. There's a function on three-dimensional space. Somewhere there's a zero. Function zero somewhere. I can try evaluating some random points and see what their signs do, if they're bigger or not. Now, if I find one that's negative and one that's positive, and I know it's a continuous function, I know there's a root somewhere, but I have no idea where it lies. It doesn't even have to lie in between those 2 points, right? So, well, what does it mean in between? It doesn't have to lie in the line in between those. So I can't bracket with a finite number of points. I could bracket with a surface, but now I do have to compute the function on the whole surface, which is an infinite number of points, and computers like doing a lot of work for you, but not infinite work. So basically, all you've left is your best guess and some sort of method that didn't need bracketing, and that was our old Newton-Raphson. So you're going to do that in multidimensional space. And that now means that you get to do things like find multidimensional derivatives, partial derivatives, inverting matrices, etc., etc. Some linear algebra will come into play here. So we're not going to go into this too much, but this is basically all you have. You have your best guess. You have maybe some sort of not real bracketing, but narrowing down, and then you do Newton-Raphson, and you hope that it converges and it doesn't blow up, because it could still blow up. Multidimensional stuff is hard from a numerical perspective. Yeah, essentially you're doing a Taylor experiment, but in all directions. So that means that's why this derivative is yeah, that's why the df dx is a matrix. Okay, so you need something to make sure that you don't run out of control. You could look at the absolute value of your function, etc., but it usually works if you're close enough to the root, but you got to know your function a bit better than 1D. Okay, so that was root finding. Optimization, kind of related. It's a little bit nicer though. So optimization is minimization or maximization of a function. So you have a function now, and you want to know where it takes its minimum, right? So we could just be lazy and say, well, let's just take the derivatives, set them to 0. Now we have a root finding problem, and we just did that. Which is true from a mathematical point of view, but it's not true from a numerical point of view, because as soon as I have more than one variable, I have this multidimensional problem now, and I'm in trouble. Also, I don't have to look at it this way. It's not just a bunch of derivatives that are 0. There are additional properties that these have, and especially in DM1, it's very, very different from the high dimension. So we're going to look at this anyway. So suppose we want to minimize. We're going to try and do something similar to this bracketing idea, but you bracket with 3 points. So if you do 3 points, you could see whether, so A, B, C, you could see if, say, the midpoint B is less than both A and C, or the functions on there is less than both A and C. And then you know, well, that would be a minimum if I look at these 3 points, right? So you get, okay, let's take the smallest one of those and keep on going, right? Until we get some sort of minimum. You could do that with a midpoint. You can also take some different values, like a golden section method is tends to be very good. So rather than just taking a midpoint between A and B, or between A and C, you take a fraction W away of that. Or you can do things like, well, I have 3 points. I can draw a quadratic curve through that, interpolate and see where the minimum of that curve is, and take it from there, right? So all of these things are very similar, except you have one extra point. You do an interpolation. You see where the next point would be. You keep on going. You keep on converging. So this idea of converging, of iterating, having a tolerance, absolute or relative, all are the same. And again, we don't have to code this in. This is in the GSL library. Okay. One issue, though, which also it's true for the roots to some extent, we might find a minimum, but there's no guarantee that this is the global minimum. So I could have a function with several minima, like this one, and I might just have picked something that, like my initial bracket might have focused on this one, and I find the minimum. Nothing will tell me that that's not the lowest point of the whole curve. It only tells me that locally I have a minimum, right? So the only way to be more sure about this is try again, right? Different starting points, so you get the same one. Now, this matters for minimization typically more than for root finding. For root finding, it was also possible, if it just draw you a curve, that you'd have something that's positive and negative, right? So there's a curve, there's a root somewhere in between. We're going to find it, but then maybe there are two more, and I just found one again. Same thing. The only way to do that is to try again. But oftentimes, finding a root is good enough. It's a solution to your problem, right? With minimization, that's often not the case. You might want to know the lowest energy state of your system, and it has to be the actual one, because nature, what you're trying to simulate, will find the real minimum, and you have not. So you fail to predict. So there's ways to get around that a little bit that work with minima, don't work so well with roots. Okay, we'll look at that. Multidimensional minimization has the same kind of problems as multidimensional root finding, but it's not as bad, basically because down is down. As long as you're okay with local minima, you can try stepping down, and you're still better than before. Whereas with root finding, you might just randomly start jumping around. You have no idea if you're closer to zero or not. Okay? So we built, typically out of 1D methods, do 1D minimizations, and do it direction by direction. So the same idea can be applied, just go in the x direction and the y direction, x direction, y direction. And hope for the best. I mean, test for convergence. So this kind of stuff could happen, right? Suppose this is a contour plot of my function, and I'm trying to find a minimum, which is obviously at the origin, but we don't know that. We started in the top right corner here, that little arrow, but the top right corner here. And then we take steps in each direction separately. Right? So we go down, do the y direction first, x direction. So these steps find sort of the minimum in that direction. And it makes sense, because if I were up again further, then I went up. So in this direction, that's the minimum. And so you take this stepped approach. And so the good news is that that will eventually, if you alternate your dimensions, your directions, will ultimately get you to the minimum. Okay, that's good. It's not bad. But it's very slow. You get this staircase. Whereas if we just took a step in this direction, right, we would get there almost with one step. So that's the idea of having conjugate gradient. So what we just looked at, that is sort of a steepest descent. Conjugate gradient tries to find the directions that you should go into, rather than just taking any direction. And so these are typically much better because they don't require as many steps. How would you do that? Well, essentially, you're going to look at this locally as if it's a quadratic equation. For a quadratic equation, I will figure out the axis of my ellipses, and I'd go along those axes. Simple. The closer you are to your minimum, the better this will work, obviously. So there's some caveats and some things that you would have to think about if you were trying to code this yourself. One of the things I really want to make clear here is that the principles of doing this, implementing Newton-Raphson, implementing this 3-point minimization, implementing conjugate gradient itself might not be that hard, but then all the special cases to make sure that things don't blow up are really hard. And so you don't have to do that. They're in the GSL library. Okay, so that's the case for using libraries and how you do it. Since we're talking about minimization, I want to end with one more technique. Remember, I told you that you're not sure if you're going to find your local minimum or your global minimum, and you want your global minimum. You want a real minimum because nature finds it. So how can we do better as numerical scientists? We just mimic nature. Nature's very good at finding the minimum. How do we do it? Look at ice. This is a perfect day if we're talking about freezing water. It's -15 outside. Water finds its crystalline structure, right, as you freeze it. How does it do that? Why does it? It's a regular arrangement. It's incredibly unlikely just find it. How does it find it? Well, because as the temperature drops, the molecules of water aren't just fixed at their random positions. They're moving around, right? They're moving around, and as the temperature drops, they're finding locally the rearrangements that are necessary. Then bigger drops or bigger conglomerates of these molecules find themselves in regular patterns, and they can do that because they move around, kind of randomly. And they can do that randomly because they have some velocity. They have some velocity because there's a temperature. So we're moving things around kind of randomly, starting off with random things. So somewhere in this random collection is going to be a nucleus of ice that is the right pattern, and it grows from there. So simulating annealing tries to mimic this idea. So here's my function. I want to have the global minimum. So where is it? This guy here. And you got to imagine putting a whole bunch of points on here, or maybe just one, and telling that point, well, just randomly go about your business. Walk around. I don't care. That's like having a high temperature where the molecules can go wherever. They go fast. They don't care about the fact that the function is a little bit lower or higher. Right? They have no problem jumping over a barrier because they have such a high velocity. And then the next thing I do is say, let's cool them down a little bit. I slow the velocity down. I make the steps less, right? I will not even show you how to do it exactly, but this is the idea. You make those points move less. You make them more aware of where the barriers are. And what that does is it actually sort of cuts off where the particles can be, or where your points can be. So when I cool them now further, they can only be in these red areas. And as I slowly cool things down, as I anneal this more and more, the only possible point I can find them is this last point. I needed these higher temperatures to get over the barriers. Barriers like this guy, right? And I needed the even higher barriers to get higher temperatures to get over here. So temperature is more, I mean, it's not real temperature. But takes the place of it, simulated. But that's what you do. And this is a way to be more sure. It's a probabilistic way, so you randomly sample things, and it's really just a matter of saying it's highly unlikely we get into the wrong one because the likelihood to be there is just so unlikely. It can happen. So you would do this more than once, but if you're truly doing this well, more than 2 times or 3 times, you shouldn't really have to do. Okay, and you'll get your minimum. Does not converge as fast as the other methods, so okay. So I should tell you that. Sorry, yeah.
Your last comment on simulated annealing, you're saying that we start from this high temperature and then gradually lower the temperature, so that we have to do everything.
No. Well, you'd have to repeat it several times if you want to be more sure. But the likelihood of being wrong is very, very low. Okay, so you could still end up stuck in one of these minimums just by chance. But the chance is exponentially proportional to the difference in basically the energy levels, if you think of it.
My concern is if you have a really rough.
Well, it depends on that depends on your problem. Yes. So there might be ways where you have to help your system or guide your system a little bit more. There might be even a system that doesn't find its true minimum even in nature. If you're looking at glasses, a prime example of where, although it would want to be crystalline, it just doesn't find that state, and it is still amorphous. And so sometimes not being able to find the minimum also happens in nature, but that's a different topic.
The reason that nature is better than
that, and the fact that it does this random motion. Yeah, this Brownian motion. Great. So GSL has simulating annealing too. So it really helps. It converges slowly. So if you don't have this problem of finding, if you have only one minimum, you wouldn't use it. But if you have this problem, it solves a lot of things. Okay. So that was it for today. Root finding, minimization, lots of different things. I will post a homework using the GSL later today. And don't forget, I should mention this, as you're doing the homework that's due today, don't all start working on SciNet 10 minutes before midnight and find that the system is busy and it takes you 10 minutes to get a node. Okay, do it in the afternoon. Any trouble, you can email us. We can help you. Okay, don't wait until the last moment for this one. Thanks.
So I'm basically trying to understand from your example how I go about building the implementing the boost.
Right.
And I guess I'm not sure which part of these things are actually necessary and which parts are.
Okay, I see what you mean.
Yes, I'm trying to kind of use it almost as like templates.
It is. So everything is pretty much needed. You don't have to do a test suite. I think that one might be optional. I have a suite of module. I'd have to look that up.
Sorry.
Yeah, no, go on. But this is your template. What you do inside it is what really matters to us, right?
So basically, you mentioned we have to build a separate file. So basically, I write some file and have a set of commands there.
Yeah.
And for the function, I'm supposed to use whatever my
like the time stepping, right? Yeah.
Yes. So if I had something like if it was like ants time step function dot cpp that I have here.
Right.
So if I have something like that, I would basically go into one of these
yeah, one of these functions, and you use that function in there. So you need a header file just a header file for that one, right? So you know,
so I need to include. So basically, I need a # include and time step function. Okay, that makes a bit sense. And so this part here, this matrix thing, that's just you defining the thing you're testing in, whereas I'm having it in two separate.
That's right. So the matrix stuff you can all drop out here, right? We're not using that.
And for testing the ants, I basically do something like this: boost require, and then some variable, like a set of variables equals.
Yeah. So what you're supposed to check is that the number of ants doesn't increase, right? So you're gonna set up a test case, preparing the arrays such that they have a certain number of ants that you know, and then call one time step and see if they have less or equal, but not more. So
and we already have like something like 1,010 ants.
You already have
set
that.
automatically. So,
but you don't necessarily have to use that initialization. You could use a simpler one if you wanted to. You could just set them all to put an ant on every block if you wanted, and just go that. That's easy. Just fill them all with ones, right? The RA has a fill routine. If you set up, just fill them all with ones. Fill the velocities with the common 1, 2. Then I can make a mistake in the initialization that would screw up anything else, right?
Yes. For executing these, I know there's the debug job thing. These are things that are executed like in a second or so. Or a second or two. Do we actually need to send them to use the?
Now for the tests you don't, but for the profiling you do, and the reason is that